All right, this movie starts with page 119. So they let f be the function given by f of x is ln of x over x for all x greater than 0. As you can see there, the domain of both, the domain of ln of x is x greater than 0, so that makes sense. And then they were nice enough and they gave you the derivative. You could have done that using the quotient rule, but. All right, part A says write an equation for the line tangent to the graph of f at x equals e squared. So tangent line equation, you really need to know this by heart. So we need to fill in y1, m, and x1. x1 is e squared. Now we need the y1 and the slope. Well, y1 is going to come from f of x. So f of e squared is ln of e squared over e squared. So that's natural log of e squared is what power, log base e is what power of e gives you e squared. Well, the power is 2. Another way to look at this is a law of logs is you are allowed to bring this exponent down. And what power of e gives you e? Well, that's 1. 2 times 1 is 2. At any rate, this would be 2 over e squared. That would be your y1. And then the slope would be gotten by f prime of e squared, which is 1 minus ln of e squared over e squared squared. So we just said ln of e squared is 2, so this is 1 minus 2, or negative 1, over e squared squared, which is e to the 4th. So there is your, oops, sorry. I meant to say negative 1 over e to the 4th here. There is your tangent line equation. Part B says find the x-coordinate of the critical point of f. Determine whether this point is a relative min, max, or neither for the function. Justify your answer. So part B, they gave us the derivative. Critical points are where the derivative equals 0 or does not exist. To take care of the does not exist part, the denominator is x squared. X squared is 0 when x is 0, but that's not in the domain. So there are no places where the derivative doesn't exist. So we're really just concerned about f prime of x being equal to 0. So the derivative was 1 minus ln of x over x squared equaling 0. Multiply both sides of the equation by x squared, and you'll get 1 minus ln of x equals 0. Adding natural log of x over, you get 1 is natural log of x, which if you're good at, you'll know that natural log of e is 1. But if you're not sure about that, this is log base e of x. So the exponent, the base grows up, becomes big. This is the power, becomes the exponent equals x. So x is equal to e. So there is your critical value. That would be like 1 point of this question. Then it says to determine whether this point is a relative min, a max, or neither. That would require us to draw a number line. And recognize that our derivative is 1 minus ln x over x squared. To plug in a number to the left of e and to the right of e. Well, to the left of e, I can plug in 1. So 1 minus ln of 1 over 1 squared. Natural log of 1 is what power of e gives you 1? The power of e that gives you 1 is 0. So 1 over 1 squared is 1. So we are positive on this interval, or the first derivative is positive. Then to the right of e would be e squared, which we just plugged in to the derivative. We came out to be negative 1 over e to the 4th, so we are negative on the right side of e. So what that means is the function climbs, gets to a max at e, and drops down. So what we can say is part B, we can say that at x equals e, we have a relative maximum. So here we go. At x equals e, f has a relative max because f prime changes from positive to negative. There's your part B. Part C says the graph of the function has 1 point of inflection. Find the x-coordinate at this point. Well, here's our f prime. Points of inflection are gotten by looking at f double prime. So part C, f prime was 1 minus ln of x over x squared. f double prime is going to be gotten by the quotient rule of that. So come over here. The high function is 1 minus ln of x. The low function is x squared. The derivative of the high function, the derivative of 1 is 0. The derivative of negative ln of x is negative 1 over x. Derivative of low is 2x. So we can figure this out. So we have low d high. Low d high, if you do this x squared times negative 1 over x is just negative x. Minus high d low, that would be 2x times 1 minus ln of x over low squared, which is x squared squared, which is x to the fourth. So here is our second derivative, which we want to set this equal to 0. So here we are. And if we want, we can distribute. You get negative x minus 2x minus 2x ln of x is 0. Combining like terms, you would get negative 3x minus 2x ln of x equal to 0. And then you can factor out an x. So you'd be left with x, negative 3 minus 2 ln of x is equal to 0. So algebraically, this would give us x equals 0. So now we have factor times factor equal to 0. So x equals 0 is not a solution. It's not in the domain of the function. So that's not an inflection point. And now we have this guy. So we're going to solve this. Bump over the 3. We get negative 2 ln of x is 3. Divide by negative 2. So ln of x is negative 3 over 2. That doesn't solve for x. Natural log means log base e. And so exponentiating this, e, the base becomes big. This is the power becomes small as the exponent. And that would be equal to x. And that would be your place. They're basically saying it has one point of inflection, find the point. It doesn't even say justify our answer. So we did it. It has to have, if it has one, if they're telling us it has one point of inflection, it has to be there. Part D we're not going to worry about because the limit got cut off. All right, next question. Here's question 120. It says let g be a continuous function with g of 2 equal to 5, and we have the graph of the derivative. Find the coordinates of the points of inflection. All right, so I'm going to take this graph g prime and make my g prime number line and my g double prime number line. G prime number line is based on, if I have a graph of g prime, this is based on whether the graph is above or below the x-axis, and this line will be based on the slope of g prime. So until we get to negative 1, we are below the x-axis. Then we get to 2, we're above. We're below to 6. And then at, looks like, it's 6, yep. And then at 7, we're above. Now, slope-wise, we are a positive slope until we get to 1. Just one thing, though. As you notice, at negative 1, we have a corner here. The slope, just want to put a little, is undefined there, and positive everywhere else on the interval. Then, from 1, at 1, the slope is technically undefined. And then goes to 4 as a negative slope. And then positive till 7. So there are our number lines. So again, points of inflection of G are going to be where G double prime changes sign. So G double prime changes its sign at 1 and 4. So at x equals 1 and 4, F has a point of inflection. I shouldn't say F, I should really say G as a point of inflection. Because, I did it again. Because G double prime changes sign. There's your part A. Part B, find the absolute maximum value of G. We're going to skip this right now. We haven't done enough math to do it. But we will come back to it. Part C, find the average rate of change of g of x on the interval -3 to 7. Part C is also a little problematic for us because Part C is asking for the average rate of change of g on the interval -3 to 7. And that would be g of 7 minus g of -3 over 7 minus -3. But we don't know values of g except for g of 2 is 5. So we're going to skip this one as well. We are going to come back to this. There is a way to figure out what g of 7 and g of -3 are. So as long as you knew that this was the appropriate thing you would need to do, that's great. Part D we can do though. It says find the average rate of change of g prime, which we have values for. So g prime, average rate of g prime from -3 to 7 would g prime of 7, minus g prime of -3 over 7 minus 3. So g prime of 7 was 1 minus g prime at -3 was -4 over, whoops, this should be 7 minus -3. 7 minus -3 is 10. So we get positive 5 over positive 10, which is 1/2. Then it says, does the mean value theorem applied on the interval -3 to 7 guarantee a value for -3 to 7 such that g double prime of c is equal to this average rate of change? The mean value theorem does not apply here because you have corners and cusps. So there are points of non-differentiability. Another way to say that, differentiability. Let's do that, sorry. There are points of non-differentiability on the interval -3 to 7. Individually, let's see. Well, at -1, 1, and 4, g double prime does not exist. Does not exist because g prime comes to a corner at those points. Hence the mean value, and the mean value theorem needs differentiability. I'm probably being very verbose here. The mean value theorem needs differentiability on the entire interval. To work. All right, next question. 121. It says, let f be the function defined by f of x is k square root of x minus ln of x for when x is greater than 0, where k is a positive constant. A, find f prime and f double prime. You got to be able to do this. So f of x is k radical x minus ln of x. Writing this a little better to take its derivative would be kx to the 1/2 minus ln of x. Whoops. Its derivative then would be kx to the, 1/2 kx to the -1/2 minus 1 over x. Which that would be good enough on the part 2 because, I mean, normally in class I would make you write this in radical form. And we're probably going to have to do it anyway. So I'm going to do it right now, but you could also, on the part 2's, left it like this. I'm going to write k over 2 radical x minus 1 over x. But now I want to take f double prime. So I'll use f prime again. It's easier in this form to take the derivative. In fact, 1 over x is x to the -1, so that's even easier. F double prime would be -1/4 k x to the -3/2 plus x to the -2. Simple application of the power rule. A better form for this would be -k over 4 square root of x cubed plus 1 over x squared. All right. I only did that because we're probably going to have to do it because they're going to ask some questions here. So it says, for what value of the constant k does f have a critical point at x equals 1? Okay, so again, critical points. Critical points are points where f prime is equal to 0 or f prime doesn't exist. So if you take a look, the derivative doesn't exist for x greater than, less than or equal to 0 because you have a radical and an x in the bottom. But they've already eliminated those values for you. So the derivative doesn't exist. I'm sorry, the derivative exists everywhere on the domain. So this doesn't happen. Kind of similar to the last problem. This doesn't happen. But f prime could be equal to 0. So we want to say f prime is equal to 0. So we have 0 equals k over 2 radical x minus 1 over x. Now, we have two variables here, but they want x to be 1. They said we find the value of k so that x equals 1 is a critical value. So now we can plug that in. We get 0 equals k over 2 square root of 1, which is 2, minus 1 over 1. So we get 0 equals k over 2 minus 1. Add 1 to both sides. 1 equals k over 2. 2 equals k. So that k value is 2 now. And then it says, for this value of k, determine whether f has a relative min, relative max, or neither at x equals 1. Justify your answer. So now our derivative, if k is 2, our derivative is kind of neat right now. Our derivative would be f prime of x would equal 2 over 2 radical x minus 1 over x, which simplifies to our derivative being 1 over radical x minus 1 over x. So we need to draw a number line for this and determine what's going on here. So I want to bracket this off at 0. 1 is the critical value. So I need a number. I'm going to pick a number to the right of 1 just so it's a little easier. If you pick 4, okay, we picked 4 for a minute. 1 over radical 4 minus 1 over 4. 1 over radical 4 is 1/2. Minus a fourth is a fourth, which is positive. So on this part of the number line, we are positive. This is f prime, by the way. And now picking a number to the left of 1 is a little tricky, but if you take a quarter, it'll be a little easier because a quarter is a perfect square. So if I took a quarter, it would be 1 over square root of a quarter minus 1 over a quarter. Well, 1 over square root of a quarter is 1 over a half. 1 over a half is 2. And 1 over a quarter is 4. So you get 2 minus 4, which is negative 2, clearly negative. So we know that f dipped down and then went back up. So at 1, we have a relative min. Because f prime changes from negative to positive. All right. Part C. This for a certain value of the constant k, the graph has a point of inflection on the x-axis. Find this value of k. Good question. All right, so now let's reset. K is not going to be 2 anymore. So that's one thing. Understand that k is not going to be 2. Or, I mean, it could be 2, but k might not be 2. So let's understand that. We might be looking for a different k value. And then they told us k has a the graph of f has a point of inflection on the x-axis. So that would mean a few things. Firstly, it would mean that this point, whatever it might be, is something comma 0. So this indicates the y value is 0. Well, in order for us to figure out inflection point, we would need to seek out the unknown x value, given the fact that the y value is 0. Okay, so where do we get x and y values from? Well, they come from the original function. So the original function was f of x is k radical x minus ln of x. There's the original function, and we know we want the y value to be 0. So here's what we know. We know 0 is equal to k radical x minus ln of x. Well, what's the other thing that we know? The other thing that we know is that since we're at an inflection point, so this guy gives us f of x equals 0. And since we're at an inflection point, we know f double prime equals 0. So f double prime, if I recall, which I don't actually, so f double prime was negative k over 4 radical x cubed plus 1 over x squared. It was negative k over 4 radical x cubed plus 1 over x squared. Let me just make sure I have that right. Good. So there's f prime of x. This also needs to be 0. So now we get two simultaneous equations in one variable. So what's the best way to go about solving this? Well, if you take a look, this equation has lots of denominators, which we could probably kill off here. So if we multiply everything by I'll multiply everything by the LCD, which would be 4 radical x cubed x squared. This times 0 is 0, which is very nice, equals, this would go away with this, and we would get negative x squared k plus 4 radical x cubed equals 0. Okay, so we could take this and solve pretty easily for k and then plug it back in over here. So let's see what we have. We'll add the x squared k over. We would get x squared k is equal to 4 square root of x cubed divided by x squared. K is 4 radical x cubed over x squared. There's your k. So going back up to here, that's k. We can plug it in. So we have 0 equals k, which is 4 radical x cubed over x squared times square root of x minus ln of x. Ooh. All right. Interesting. X cubed times x is x to the 4th. Okay? So we get 4 square root of x to the 4th over x squared minus ln of x. But square root of x to the 4th, so long as x is positive, is just x squared. So 4 over x squared, as long as x is not 0, which it can't be, is 4. Adding natural log of x to both sides, ln of x is 4, which makes log base e of x 4, which makes e to the 4th equal x. There would our x value be. And did we do everything? We found the value of k. Actually, so we found the value of x. We found the value of x to be e to the 4th. And k would be 4 square root of e to the 4th cube, which is e to the 12th, over e to the 4th square, which is e to the 8th. And I would leave this like this and be done. That is a hard problem. That's something that's making me think. That would be very avoidable on your midterm. I wouldn't put anything on there that nasty, but this was an AP question, and these are the questions that separate, what I would say the 5s from the 5 pluses. The type of question this is. Whoops. All right. 123, we let h be a function defined, and we have the derivative of h given for every x not equal to 0. We want to find all values of x for which the graph has a horizontal tangent. Horizontal tangent means A horizontal tangent means f prime, or in this case, h prime is equal to 0. So x squared minus 2 over x equal to 0. Well, that would mean x squared minus 2 equal to 0. That would mean x squared is 2, and x would be plus or minus a radical 2. And then it says, we want to determine whether h is a local max, min, or neither of these values. This is a tricky question for the following reason. When you draw your h prime number line, you need to include negative radical 2, but you also need to include 0, because 0 makes the derivative undefined. It's a critical value. So even though the derivative doesn't exist there, the derivative could possibly change signs there. So you need to be very careful. So we have x squared minus 2 over x. So picking a number to the left of negative radical 2, say 2. Sorry, negative 2. Negative 2 squared is 4. 4 minus 2 is 2. Divided by negative 2 is a negative. So on this interval, the derivative is negative. Picking a number on this interval, this new interval, I'll pick negative 1. Negative 1 squared is 1. Minus 2 is negative 1. Divided by negative 1 is positive. So what happens is you might pick 0. 0, the derivative doesn't come out right. But then you might pick a different number, like between 0 and radical 2, to represent that interval that we just did. And you're going to get a sign. You're going to get a bad sign on that interval if you don't include 0 on your number line, because of 0 being a place where the derivative is undefined. So picking a number between 0 and radical 2, I'll pick 1. 1 squared is 1 minus 2 is negative 1 over positive 1, which gives you a different sign, negative. Then radical 2, past radical 2, we have 2. 2 squared is 4 minus 2 is 2. Divided by 2 is positive. So at negative radical 2, we have a min. At 0, we don't know exactly what we have at 0, because we don't even know if the graph is defined at this particular moment. And at root 2, we also have a minimum. So at x equals positive and minus root 2, h has a local minimum I think I did minimum, which is no good. Minimum. Because, well, h prime changes from negative to positive. All right, there's part A. Part B says, on what intervals is the graph concave up? So concave up, we're looking for f double prime to be greater than 0. That would require us to find f double prime. Of course, I keep saying f and it's really h, and I know that's not a big deal, but it kind of is. So here's h prime. It was x squared minus 2 over x. To find h double prime, we will use the quotient rule, take the second derivative. So h double prime, let's see. We have our high is x squared minus 2. Our low is x. H prime is 2x. Low prime is 1. And we'll make this happen. So low d high would be 2x squared minus high d low, which is minus parentheses x squared minus 2. Please use the parentheses. This is coming with two terms. Over low square, which is x squared. So our second derivative turns out to be x squared plus 2 over x squared. Interesting. So there's our second derivative, and we want to find where this function's concave up. So we have our number line, and again, second derivative does not exist at 0. Important to put that on the number line. And then we'd also want to find out where the whole thing equals 0. Cross multiplying, we'd x squared plus 2 equals 0. But if you think about this for a moment, x squared is at least 0. If not bigger, plus 2 can never be 0, so this has no solutions. So the only place where you can come up with an inflection point here would be at 0. So x squared plus 2, again, think about this. X squared plus 2 is always a positive quantity. X squared, besides at 0, is always positive. So this function's second derivative is always positive. So if you look, I mean, if h double prime is always positive, you're always concave up. So to write our answer carefully here, h is concave up on negative infinity to 0, union 0 to infinity. I'm skipping 0 because it is not in the domain of the function. So you need to skip it. That's a very technical point, but you do need to skip it because h double prime is positive on that interval, or on that set. All right, next question, part C. Write an equation for the tangent line of the graph of h at x equals 4. Let's keep in mind that h of 4 was negative 3. Part C is very easy. Part C, we have y minus y1 equals m times x minus x1. They told us h of 4 was negative 3. So this is positive 3 equals the slope times x minus 4. The slope would be had by h prime, which was x squared minus 2 over x. So the slope at 4 would be 4 squared minus 2 over 4. 4 squared is 16 minus 2 is 14 over 4. 14 over 4 is better known as 7 halves, but you would not need to simplify on the part 2. 7 halves, put it here, done. Very easy. Part D is a little more challenging. Does the line tangent to the graph at x equals 4 lie above or below the graph of h for x greater than 4y? Well, if we think about what's happening, when h is 4, we know the function's increasing because the first derivative is positive. And then we also know the function's concave up. So if you think about what's happening here, regardless of what kind of curve, what kind of function we're dealing with, we know at x equals 4, we have this type of curve. We have an increasing concave up curve. So this tangent line, a tangent line has to lie below an increasing concave up curve. In fact, even a decreasing concave up curve, the tangent line would lie below. It's concave down curves that tangent lines lie above. So that's why they're asking you about concavity. Part D is supposed to kind of make you think about the concave issue. So since h is concave up, at x equals 4, the tangent line lies below the curve. And we're done. Like that question. All right, we've done this one before. I almost feel like skipping it, but I'll do it anyway. We have a function that's continuous on the interval. We have all this great stuff about the function. We want to create number lines here. So here's f prime. From 0 to 1, close this off. From 0 to 1, the derivative is positive. At 1, the derivative is still positive. So at 1, the derivative is 0, but it's still positive until we get to 2. Then it's undefined, doesn't exist. Then it's negative through 4. F double prime from 0 to 1, second derivative is negative. Then it's 0 at 1, positive till you get to 2, undefined at 2, then negative till 3, 0 is out at 3, and then it's positive to 4. So there's our number line for f prime, number line for f double prime, all nice and filled in. So it says from 0 to 4, Justify whether we have final values of x at which f has a relative extremum. Notice they're not including the endpoints. So f is increasing until we get to 1, then decreases until we get to 4. I'm sorry, not 1, 2. So part A is at x equals 2, f has a relative maximum because f prime changes from positive to negative. And then part B, they say just sketch this graph. So if you think about it, from 0 to 1, we have increasing concave down curve. So if you kind of try to figure out what f looks like, and by the way, we're not doing part C. So actually, I'm going to get some white out here and kill this off so I can write here. Whoa. We're not doing part C. So let's take a look. It says, on the axes provided, sketch the graph of the function with all characteristics of x. So from 0 to 1, we're increasing concave down. So we look something like this. And then we're increasing concave up. So it looks something like this. Then at 2, we start to decrease and be concave down. So we're looking at something that does this. And notice the derivative at 2 can't be defined. So it can't be smooth here. We have to have a corner or a cusp, or as some of you have commented in the past on this question, it looks like a shark fin. So, and then from 3 to 4, we have our function still decreasing, but we're concaved up now. So it looks something like this. Now, the other thing that we have to understand is that they gave us function values. So at 0, we're at -1. At 1, we're at 0. At 2, we're at 2. So the shark fin happens at y equals 2. At 3, we're at 0. And at 4, we don't know. So here's our general function. Looks something like this. Something like this would work. All right, moving on to the next question, I suppose. 128. A coffee pot has the shape of a cylinder with radius 5 inches as shown in the figure above. Let h be the depth of the coffee in the pot measured in inches, where h is the function of time.